Welcome to Lecture 12A, entitled Changes of Variables in Multiple Integrals. And this is for 2D systems, in other words, things that appear in a plane. So this is actually new material now, and this material can be found in section 16.7 of the text, and reading assignment 2, reference material meaning from objective 3. Also, you will find some of this material relevant to Introduction to Lecture 8 on Jacobians, which we talked about earlier. And you might want to review parts of Lectures 1A and 1C. So the objectives of this lecture are to figure out how to change integration limits and differential area for double integrals with a change of variables. The reason you would do this is to simplify the integration if it's too difficult to perform in Cartesian coordinates. And so the concepts and visualization skills in this particular lecture module are the relationship between integration bounds in Cartesian coordinates and the transformed coordinates, and determining the determinant of the Jacobian matrix and differential area in the transformed coordinates. Note 1, in the remaining lecture modules on integration, we use different nomenclature to find transformation matrices compared to what was discussed at the beginning of Lecture 8. And we're doing this to be more consistent with the textbook. Second note is you may find Lecture 1A Slide 6 and Lecture 1C Slide 4 complementary to the discussion in this lecture. So as usual, the second slide is just a review of the slides to follow, so I won't bother basically spending any time on this slide and move on to the next slide. All right, so sort of as a preamble to looking at multivariable integration with change of variables, which would mean 2 variables, and in the next lecture, 3 variables, we want to review some of the things related to change of variables for 1 variable, and also basically make the connection at this point to the Jacobian, which was not introduced last year because it wasn't necessary, but here we can. So we're going to use a method of substitution and the relationship to the magnitude determinant of the Jacobian here to make that connection. And so we start by computing the integral of f of x dx from 0 to 1, where f of x is 2 times the square root of 2x plus 1. And a figure of this particular function integrand is what you see over here. And so we're interested in computing the area that's shown in blue here. And so this integral is a little bit problematic. So the simplest thing to do is to take a guess at what sort of variable what variable substitution to use. So in this case, we've chosen u equal 2x plus 1 as a sort of change of variable. And we can then express x in terms of u just by inverting this expression. We'll need that information later, but I'm just putting it here for now. We need to also compute the relationship between du and dx. So if I take the derivative with respect to u here, then that just becomes du equals 2 dx, or dx is 1/2 du. All right? So if we're going to change variables, we also have to change the integration bounds. So the integration bounds for x equals 0 and x equals 1, we now have to find the corresponding integration bounds in terms of u. And so we can make use of the information that's here. We know that u is 2x plus 1. And so if you put u equals 0, x equals 0 in, you would get a lower bound, which would be u equals 1. And if you put x equals 1 in here, which was the upper bound with respect to x, then this becomes 3, which you see here. Okay, so this is really what we've done. And so now we can substitute in for the integrand and the differential dx. And so you end up with this expression here, which simplifies because the 2's cancel, and we end up with this integral, which is a very simple integral. So if you look at this particular functional, which is what you see here, this is u now in this direction, y in this direction, but you're integrating between 1 and 3. Turns out the area that you see here is equivalent to the area that you see here. But this integral is much, much easier to compute. All right, so that's just the note that I've made over here. All right, so now we make the connection to the Jacobian. We've just gone through an illustration, and now let's see how we can relate this to a Jacobian. Well, the first thing we do is we're going to just let x be some function of u. Just keep it very generic. And we're going to define dx by du, which is the partial derivative, but it's on a 1-by-1 Jacobian matrix because there's only one variable right? There's a mapping between x's and u, or u's to x's. And so this is just a one-by-one Jacobian. Remember, Jacobians involve partial derivatives. In this case, it's a direct derivative because there is only one derivative. Right? Turns out this is a scalar. So the matrix in this case, one by one, is by definition a scalar. So basically we can say the determinant of the scalar is the scalar. And so the Jacobian matrix in this case would be dx du. All right, so now let's go back and look what we originally had here. X is 1/2 u minus 1. This is the reason why I did the computation here, right? And this is g of u. So if I take dx du, I get 1/2. So now let's go back and look at this expression. We have 2 root 2x plus 1 dx. We made this substitution, but we could also leave this in a generic form where x was g of u and dx just turned out to be this, 1/2 du. So the 1/2 is dx du, which we had defined back here as a Jacobian. So you'll notice here this just becomes the determinant of a Jacobian times du in the new transform system. So this basic idea will actually will be transferred to the notion of multivariable as well, except in that case the J will actually be a matrix, a proper matrix, but we'll still be taking the determinant. All right, so now we're dealing with mappings, in 2D. So we have two domains. We have the domain R, which is the one involving x and y, and a new domain involving u and v. So this is a two-variable case that we're looking at. So what we're going to do here is we're going to have some domain, which is in terms of u and v. It's two-dimensional. And we have points in the domain u and v, which map to points in R, which are points x and y. And this is the transformation matrix we're dealing with. So why is the mapping required? Well, it maps points from the interior region of R to the interior region of S. I mean, we can go back and forth if you want. Here it's shown from S to R, but it can also be from R to S. Maps points that bound region R to points that bound region S. So if we're interested in what is the boundary of this region S and how does it relate to the boundary of R, that'll be necessary because if we're going to do integration, we need to know the boundaries that we're going to be dealing with. So we need that information. And thirdly is to map differential areas in region R to differential areas in region S. So the shape of the differential area here relative to the shape of the differential area here are not necessarily the same. And so what does that mapping look like between the differential areas? All right, so now what are the transformations required for integration? Well, this is where x and y are functions to u and v. And this transformation is useful for understanding how to map points from the S-plane to the R-plane and to map differential area in the S-plane to a differential area in the R-plane. This is just a statement of fact for now, but you do need this information. Without it, you cannot do these calculations, which are necessary. And if you take the inverse, which means you express u in terms of x and y and v in terms of x and y, this transformation is useful for understanding how to map points from the R-plane to points in the S-plane. So typically you're given these points and you want to figure out what they would look like in the S-plane. So you'll need this transformation. So in any event, if you want to solve this problem, you need the boundary points and you need differential areas, which you need both of these transformations. It could be that you have one transformation, but it's next to impossible to compute the inverse. So keep that in mind, because if you cannot, then you maybe have made a bad choice, or maybe, in fact, it's very difficult to find a suitable transformation. All right, so let's take an example. We're going to transform a square which is in the UV plane, and the square has dimensions 0 to 1 in U and 0 to 1 in V, so it's a unit square. And we want to find the image of S in the XY plane under the following transformation. We let x equals u squared minus v squared and y equals 2uv. So the simplest way to set this thing up is to set up a table where every side of the boundary is given a separate row. So if you'll notice here, you've got this, 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 and this, and I've color-coded them. This line segment is blue, this line segment is yellow, this is red, and the last one is black. And this contour basically bounds the region of interest. And so what we'd like to know is if this is what it looks like in the U plane, what does it look like on the XY plane? So this will get mapped into some curve in the xy plane. So will this, so will this, and so will this. And so now basically we just go through each one of these in turn. So the blue segment would be this. The blue segment's when 0 is less than equal to u is less than equal to 1 and v equals 0. The yellow segment is the vertical segment where u is fixed at 1 and v can range from 0 to 1. This segment here is when v is fixed at 1 and u can range from 0 to 1. And the last is where u is held at 0 and v can go from 0 to 1. And now what we want to do is to transform those boundaries in the UV plane to boundaries in the XY plane. And so what we do now is make use of the transformations here for each one of these rows. So for the first case, basically, v equals 0. If v equals 0, then y equals 0, and x becomes u squared. So that's what you see here. For this segment, u equals 1. If u equals 1, y equals 2v, right? And u is 1 here, makes this 1 minus v squared. So that's why you see this. The third would be v equals 1. So this becomes y equals 2u. And this becomes u squared minus 1, which is the row that you see here. And lastly, u equals 0 would mean y equals 0 and x equals minus v squared, which is what you see here. So there's a very sort of procedural way of doing these things. So the next thing basically is to figure out what this represents in terms of the xy domain. Right? If x equals u squared and u ranges from 0 to 1, right? That means x must range from 0 to 1. So that's the range of x, and y equals 0. So that's the first one down. For the second one, it's a little more tricky because we want y as a function of x. So you can either you can either start here. You can start here, for instance, say if I take the square of this, and if I divide it then by 4, that'd be y squared over 4, then end up with v squared. If I now take 1 minus that, then I end up basically with x. And so now you get an expression between x and a y, and if you simplify, that is bring y over to the other side, then you'll end up with y equals 2 square root of 1 minus x. So that's making a relationship between these two in terms of isolating y in terms of x. X will be from 0 to 1, and the reason being that if you look at 1 minus v squared, v ranges from 0 to 1, which means x will be ranging from 1 to 0. Or just in simple terms, 0 is less than equal to x is less than equal to 1. All right, for this case here, basically, similar situation as before. We have to express y in terms of x. So you could square this and then divide by 4, and then basically minus 1, and that would be equivalent to x. And then simplify in terms of y, and you end up with the expression that you see here. In this case, though, x would be ranging from minus 1 to 0. And why is that? Because u is ranging from 0 to 1. If u equals 0, x is minus 1. If u equals 1, it's 0. That's why we have this. And lastly, we have this situation, y equals 0, x equals minus v squared. And v in this case is ranging from 0 to 1, so that means x is ranging from minus 1 to 0. So now we have all of these in a desired form, and we can graph them. So for instance, here, from 0 is less than x is less than equal to 1. Right, which would be the section that you see here. This is the blue line. This 0 is less than equal to x is less than 1. Y equals 2 square root 1 minus x. That's the yellow line, which is this. For minus 1 less than x is less than 0, it's y equals 2 square root 1 plus x, which is this line. And lastly, for the last segment, minus 1 is less than equal to x is less than 0, y equals 0, which is this. So this object transforms into this object. If you want to look at this in more detail, there's an interactive version here or here. There's not really much to play with. It's just to show you basically where the graphs came from. So this is a procedure. All right, so the next thing is we know how to map the boundaries. How do we map differential areas? And so we want to justify that dx dy becomes the determinant of the matrix J du dv. And so there are two ways of looking at it. This one's purely based on vectors, but it doesn't give you much insight in terms of how to relate pictures, but it's perfectly okay. So if I have a differential area in Cartesian coordinate system, where I have the vector along the x direction as being dx x hat, and along the y direction dy y hat, and if I take their cross product and take the magnitude, that's equivalent to the area, the differential area dx dy. So this is more or less a proper, correct statement in terms of, from geometry. This is the differential area. We now look at a transformation of variables where we say let x be u, u, v, h be function h of u and v. And I'm just putting on the side here the definition of the Jacobian. That's the determinant of the Jacobian. The Jacobian matrix would be to take the derivatives of this with respect to u and v, and to take the derivatives of this with respect to u and v, which is what I've done here. All right, so the row and the second row. And then you take the determinant of this matrix. So this symbology is more or less what we're trying to do here. Take the determinant of this 2 by 2 matrix. All right, so now if we look at this diagram, we can basically say that if we had some arbitrary vector ds, a small differential vector, then that differential vector would be some linear combination of the x hat vector and the y hat vector in a Cartesian coordinate system. But let's say we have a new coordinate system where you have these variables u and v, and you're going to have basically the direction, the tangent vector to the u would be the u hat, and to v would be v hat. These two vectors do not have to be orthogonal to each other. I just labeled them as arbitrary at this point. All right, so in effect, what we can say is that if you're given the dx x hat, you can also write that as a linear combination of the u hat and v hat vectors. But how do you do that? Well, you do a first order linear approximation of these functions using a Taylor expansions. So the delta x becomes the dx. And so this is a dx x hat is the partial derivative with respect to u holding u and v constant du. So this is a measure of length. U hat plus dg dv holding u and v constant at a specific value, which is the corresponding coordinates in the new coordinate system that's at u0 and v0 at this location. dv is basically, this becomes the length in the v direction. You can do the same thing with y. In this case, we're dealing with the second function. And again, everything looks similar. And now you take this, which is basically this vector, and this, which is this vector. But this new vector, u hat, v hat, there are two components, whereas here, this had no y component, and this had no x component. So if you put these together, you can write them out. What you're doing is you're taking this vector, which represents the dx vector, dx x hat, cross product with the y hat vector dy. And if you work that out, you end up with this expression du dv. But this is nothing more than taking this expression and working it out. So effectively, we've just proved that it takes on this form. Okay? So again, just to remind you, this is the definition of the cross product in the new coordinate system. All right, so this is more of a mathematical exercise, but we can actually look at this from a geometric standpoint, and it's actually a little bit easier to understand. So this is actually taken from a textbook, and I'll make note of it in the next slide. So here we start with basically in the UV plane a tiny little square or rectangle with measurement delta U here, delta V here. Evaluate at this point is U0, V0. And if we were to go along this line, this would be with U held fixed at U0. If we go along this line, it would be with V held fixed at V equals V0. And then we have our transformation matrix, which takes on this form. So the difference here now is we're going to use a position vector. And this position vector, R, right, this will be the X value component and the Y value component. And so if you were to take this and map out going along this direction or map out going along this direction, this would be the position vector that would be basically scanned if you were to hold V0 constant and apply this. This would be the position vector that you would scan if you hold U fixed and scan in this direction, which means V is changing. All right, so this is a region that's being mapped out, all right, by the position vector. All right, but I want the tangent vector here. Why? Because I'm going to make use again of a nice little expression relating the area to vectors. So this vector here, right, and this vector here need to be determined. And so in this picture down here, we see RU at position, R at position U0, V0, here at U0, V0 plus delta V. And I'm going to call that vector B. So this is in the limits going to be a tangent vector, right? And similarly here, this is basically holding V0 fixed, and this is going to be the vector A, which will be a tangent vector for this particular line segment. Okay, so I can also then say, well, wait a minute, if I take this and divide by delta v and multiply by delta v and let delta v go to 0, right, then essentially end up with a partial derivative with respect to v times delta v for this side, and a partial derivative with respect to u times delta u on this side. So the book uses delta u. I've used du. More or less they're synonymous, but in the limit this would become du. And see, ru basically is just dr du, and r subscript v is dr dv. All right, so this is then the length of side A, basically written out, and this is the length of side B, written out. So the next step basically is to make use of the notion of the cross product and its magnitude. And what would that represent? It would represent the differential area of this green region. All right, so that's an area of a parallelogram. And so let's do this computation. I'm basically taking this, and this is a typical format. IJK, first row would be this vector, second row would be, third row would be this vector. So if you work this out, take the determinant, you end up with this expression, okay? But if I take its magnitude, well, the k is gone, it's just going to be whatever is preceding the k. And so we end up with this. But lo and behold, this is exactly as before. We can write this as a matrix, a 2 by 2 matrix, if it's take its determinant, and this is equivalent to this. But here we have a pictorial sense of what we're doing. And so, in fact, intuitive, it's a little bit easier to grasp. If you want a more detailed treatment using this method, you can go to chapter 1510 of the book by Stewart, 70 Calculus, and the pictures have been taken from this textbook. If you want to look in more depth to where the book is available, you can just look at this URL. All right, so a change of variables for double integrals. So this is now the basic theorem. We're now ready to compute the double integral with the change of variables. And so, of course, certain rules have to be basically in place. So you have a transformation matrix, a transformation equations, and your transformation that maps a closed bounded region S in the UV plane to a region R in the XY plane, and assume T is a 1-to-1 on the interior of S, and G and H have continuous first partial derivatives there. If F is continuous in R, then we basically say this integral, which was in a Cartesian coordinate reference frame, is this integral now in a transformed reference frame. So here is the new differential area. And of course, anywhere you see X, this gets replaced by GUV. Anywhere you see Y gets replaced by HUV. So this new function is only going to be a function UV. And of course, the boundaries on this will have to be transformed into boundaries involving U and V. Okay, in the integral over R, dA corresponds to dx dy. In the integral over S, dA corresponds to du dv. The relation dx dy to j du dv is the analog of du equals g prime x dx in a change of variable with one variable. All right, so just a couple of notes here. Note one, in the textbook, they show the absolute value of the determinant of the Jacobian matrix as this, okay, which, I mean, if you don't look carefully, you wouldn't know that. And the actual practice is described in the book is to compute the determinant of the Jacobian matrix and then take its absolute value. So keep that in mind. Now, why? Well, it's an artifact that arises as a result of confusion between a right-handed and a left-handed coordinate system. Opposing an absolute value guarantees that the result is always positive, as it should be. So even if you don't even realize that you're dealing with a left-hand coordinate system, it doesn't matter because you're forcing the answer to be zero, to be positive. Okay, so reason why the book uses the absolute value of the determinant of the Jacobian matrix. Here's a perfect example of how the problem arises. We have, so let's say, x equals GUV, y equals HUV, or alternatively, what we could do is just swap these two, okay? When you set it up, you have really no idea of what you're going to be doing. You just do something and hope that it's right-handed. Anyway, you can also write it this way, all right? So if we take the determinant of the Jacobian matrices, for this case, this is the setup, and you get this. But if you do it for the second case, you end up basically with the negative of the value that you originally had. So in some case, you get a positive. In some case, you get a negative. So which is correct? All right, that's basically the question that comes up. Well, again, this is the distinction between right-hand and left-hand coordinate systems that we need to basically make you aware of. We want a positive number. It makes sense So by taking the absolute value, we can guarantee the desired result. If the transformation is formulated as a right-handed coordinate system in the transformed system, then the determinant of the Jacobian matrix will always be positive. So that's your takeaway message. All right, so we'll do an example now, integration bounds in polar coordinates. It's sort of familiar with. So we're going to let x equal g of v, but we're going to use different variables. Instead of u and v, we're going to use r and theta because you're basically familiar with them. And this will be r cosine theta, and y will be r sine theta. And so now what we want to do is first find the integration bounds, and then figure out what the new differential area looks like. And so let's look at what happens in the r theta plane versus what happens in the yx plane. All right, so if we were looking, for instance, at this particular example here, right, where you've got this square, in the boundary of the s in the r theta plane, right, and boundary of the r in the xy plane, let's start basically in the r theta plane, all right? We have segment A, which is here, and this is r, direction r, this is direction theta. So r basically can go from 0 to 1, and theta basically goes from 0 to pi over 2. And so there are 4 segments to the boundary here, okay? Now here you would say, wait a minute, there are only 3 segments, 1, 2, 3. But be careful, the origin basically is taken also to be a possible point. And in fact, the fact that you have multiple mappings to a point really doesn't change the problem. We're only concerned that it's a one-to-one mapping within the region itself. So let's look at the transformation equations. Okay, so let's take the first case. If we're going from here to here, r is between 0 and 1 and theta is equal to 0. In that case, x is equal to r and y equals to 0. Okay. We also know that if you take the square of this and the square of this and add it, you get r squared. Okay, or that's equivalent to x squared plus y squared. So that's more or less the equation of a circle if you just looked at that and not with putting any limits on theta. Okay, so x equals r, y equals 0. So in this case, basically, we would say that this transforms, given that we have x equals r equals theta. That means that x goes from 0 to 1 and y equals 0. So that would be for the segment A. For the segment B, r is 1, and 0 goes from theta to pi by 2. So that's along this line here. In this case, x is cos theta, since r equals 1, y equals sine theta, since r equals 1. So this basically just becomes the equation of a circle, and it turns out it's only the quarter circle. Why? Because 0 is between x and 1. All right, so this just becomes y equals the square root of 1 minus x squared. Okay. Third would be going along this region. How does that transform? So in this case, r is ranging from 0 to 1, theta is at pi over 2. So in this case, x becomes 0, since cos of pi by 2 is 0, and y just becomes r. So in this case, basically, for c prime, which would be along this line now, x will be equal to 0, and y can range from 0 to 1, right, because of this. Okay, y equals r, right, and r can range from 0 to 1. Okay, so that's why 0 is less than equal to y is less than equal to 1. And the last thing is r equals 0, 0 less than theta equals less than pi by 2. In this case, x equals 0 and y equals 0. Well, that would mean we're right at the origin. That means that for every value of theta, right, as you move along here, you constantly map a point to the origin. But it's the boundary, so it doesn't matter. In the theorem, it doesn't matter about the boundary. All that matters is it's one-to-one within the region enclosed by the boundary. So more or less, that's how we transform this boundary into this boundary. Okay, so this is just a note saying how we got basically to this expression here, just making use of this. All right, so let's take an example. Let's say compute the following integral, but we're going to use polar coordinates. So the first thing we will do is we basically compute the Jacobian. So this would be x equals r cosine theta, y equals r sine theta. Dx dr is cos theta, dx d theta is minus r theta, dy dr is sine theta, dy d theta is r cos theta. And now we set up the Jacobian matrix, and it has this form. And we take its determinant. If you take its determinant, its value will be equal to r. So that means basically dx dy maps to r dr d theta. So that just becomes the mapping. What about the integration bounds? Well, from the previous slide, right, just looking at this integration of Cartesian is this. Okay, it's the same. And this basically, when mapped to the r theta plane, would look like this. So that's 0 less than r is less than 1, and 0 less than equal to theta is less than pi by 2. So this integral, therefore, gets transformed into this integral. And since x is r cos theta, y is r sine theta, if you substitute in minus x squared minus y squared, this becomes minus r squared. And so you see here 1 minus r squared. And the j dr d theta, this j determinant becomes r, which is what you see here. And so now you have the complete integral in the transformed system. If you evaluate this, you'll end up with this expression here. Note, again, what I've done here is I've shown basically the bounds. So there's a bound on y. That's the upper bound. That's the lower bound on y, which is at y equals 0. That's down here. And the bounds on x would be from 0 to 1, which would be x equals 0 is along here, and x equals 1 would be along there. All right, so that concludes Lecture 12A. Thank you for listening.